Alrighty, let's go ahead and get this homework taken care of. So 3 ionic compounds, soluble, 3 ionic compounds not soluble. So no, you can't use the ion more than one time. So somebody give me a soluble ionic compound.
NH4
NH4 something.
NH4OH.
NH4OH. Got to be soluble, right? The hydroxide doesn't want to be, but it doesn't matter because the ammonia lets go. And that's really the key. Is one of them going to let go? If it lets go, then the other one doesn't have anything to say about it, right? He already let go. Okay, now we're automatically ions. So give me another one that's soluble. Slightly more. Sure. One more?
Lithium nitrate.
Lithium nitrate. Okay, all of those guys are all soluble. Now give me 3 insoluble ones. What? No. 2 reasons why that's wrong. 1, we already used lithium, so you can't use it again. 2, lithium's never insoluble. The carbonate sounded good, but the lithium cannot be combined with that. Silver carbonate? Sure, silver carbonate would work. Something else that's insoluble?
Copper hydroxide.
You already used hydroxide.
Mercury 1 iodide.
Sure. The iodide rule says it's soluble, but it's 1 lower than the mercury 1 rule that says it's insoluble. So this would be insoluble. Another one?
Lead oxide.
Lead. Which one?
Oh, yeah, that 2.
Lead 2 oxide. That works. For sure. Okay. Let's move on to this one. So what do we have for names, first off? The first one? All right, so we got some magnesium bromide and some silver nitrates. What else we got? And okay, let's go ahead and balance it. What do we need? I need a 2 in front of the silver bromide to balance out my bromides, right? Then I need a 2 in front of the silver nitrate to balance out the silvers now. And then that takes care of my nitrates, doesn't it? Okay, states? The first one? No. No. What are your options? Okay, solid or aqueous. And this is an example of what kind of problem?
Oh, bromide arsine. Who?
This describing reactions in water? That's what kind of problem we're talking about here. So,
Yeah, how are we supposed to know that?
because we have a heading called problems in water, and so problems that look like this.
In water at all.
In the notes, I'm saying. And when we went over it in the notes, we talked about ionic compounds like this. Anytime you're going to see how about this for a second? If that was a solid, what would it look like generally? What kind of compound is it? What kind of compound is it? It's an ionic compound, right? Okay, and this? Ionic. So if these are both ionic compounds and they're solids, what do they look like? Great. More information.
Like a metal?
No, they do not look anything like a metal. What are these things? What's the general name for ionic compounds? Salts. So what do these things look like? Salts, right? They're different colored salts. They're white, like table salt. They're blue, like copper salts. They're yellow. They're any color you could possibly think of colored salts. So if you were to take two salts and mix them together, would they react very well? They wouldn't, would they? Just like two solids, they can't react with each other very well. Why?
Can't separate and mix back together.
Right, only their surfaces can touch, and maybe they'll react. So when I see a compound like this, and what we had was an absolute switching of the cations and anions, how must that be occurring?
In water.
So your two options are it's either aqueous or it's a solid. Could this reaction happen if they were solids?
No.
No.
So that's just something we're supposed to intuitively know, or now we know?
We talked about it when we did the reactions in water, but now you know for sure.
Okay.
So, I mean, does that make sense? If you took baking soda and table salt and mixed them together in a bowl, would you expect them to start reacting with each other?
No.
What if you got them wet? Yeah, they dissolve and then they could react. So they physically can't even do anything until they become aqueous. So if you can't dissolve table salt, is it salty?
No.
If you were completely dry mouth and you threw salt in your mouth, would you taste salt? You wouldn't taste anything at all. Okay, so you can't have anything happening until what do they need to do to each other? They need to let go, right? The ions need to let go and then they can recombine. But the first thing they have to do is let go, and they can't let go if they're solids. So when you see this kind of reaction, so what do I have up here? An ionic turning into what? An ionic and an ionic. And we're going to find probably today, yeah, we'll talk about today, that this is called a double replacement reaction. These only happen in water. So what's the state for the magnesium bromide?
Aqueous.
Why is it aqueous?
It's in water.
It's in water and bromides are soluble. We don't have a magnesium rule, but we have a bromide rule. And how about the silver nitrate?
Solid.
No. Why is this one aqueous? What's soluble? The nitrate soluble. So even though the silver is wanting to be a solid, it's below the nitrate rule, so it gets to be aqueous. And so then on the other side, magnesium nitrate? Aqueous, right? We don't have a magnesium rule, and we just said that the nitrates were soluble. And then the last one? It's a solid. Why is this one a solid? Silver's rule says it's solid, and bromine's rule says it's insoluble. Sorry, it says it's soluble, but bromine is lower on the list than the silver, so the silver rule supersedes. So this guy's going to be solid. Okay. So now, what's the full ionic equation look like? Mg plus 2 aqueous plus 2 Br negatives aqueous. Now it's really important that you write 2 Br negatives instead of what? Br2, because the 2 Br negative means 2 bromide ions independent of each other, and the Br2 means one molecule of bromine, of 2 bromine atoms that are stuck together with a -1 charge, which is not what's going on here. Yeah?
Bromine is also liquid on the periodic table, so is it a liquid when it's
Bromine, what is a liquid?
bromine?
Bromine, right. What do you have?
Bromide,
Which is what?
aqueous, I guess.
I mean, what is
I don't
bromide?
understand the difference.
What is bromide?
Oh, an ion.
An ion. So once it's an ion, all the rules about the atoms disappear, right? I mean, sodium atom is explosive, and sodium ion is not. And so bromine element, the atom itself, is a liquid at room temp. But when it turns into an ion, it's everything's different. So then we have 2 silvers that are aqueous with a plus charge, and we've got 2 nitrates that are aqueous with a minus charge. Why did it do that? And then an arrow. Okay, so now we've got magnesium and bromides, silvers and nitrates, and I take them and I mix them all in the same container. And when that happens, now all the pluses and minuses can run into each other. And when that happens, what happens when the magnesium and nitrates run into each other?
Stick together?
No.
Did you write that? Did you write that they stuck together?
No.
What did you write? What did we write just now? We said that they're aqueous, right? And any of these ions up here that say aqueous, those ionic molecules, what does that technically mean? More specific than that. It's not that they are soluble in water, it's that they already dissolved. They're already gone. They've already separated out from each other. That top line up there, I wrote the magnesium nitrate together for simplicity's sake, to make it smaller. But in reality, once I write the AQ, what does that mean? They're already separate. So when they ran into each other, the magnesium and the nitrate ran into each other, what happened? They bounced off of each other because the nitrates are soluble. And they're in water, so why would the nitrate grab a hold of something and make a solid? It won't. So then I still have magnesium with a +2 charge that's aqueous, and I have 2 nitrates that are aqueous with a negative charge.
So I have a quick question. With
Yo.
the balanced equation and like how everything transfers, so if you have a coefficient in front of a whole compound,
Yep,
that number gets like distributed.
yep.
But if you have a subscript, that number just applies to only that. Okay.
So in that first one up there, we have the magnesium bromide, so there's a coefficient of 1 in front of that. So I just have 1 magnesium, but there were 2 bromides in the compound, so then it becomes 2 bromides. If there was a 2 in front of the magnesium bromide, then there'd be 2 magnesiums and 4 bromides. But what happened when the silver and the bromine ran into each other? They stuck together. So then I've got a silver bromide solid.
Do you have to write a 2? Or no?
I do need to write it too. Yep, sorry. So the full ionic equation is still balanced. I still have 2 and 2 and 1 of the magnesiums. Alrighty, so what did nothing in this chemical reaction? This magnesium right here and this magnesium right here, they're the same thing. Nothing about them has changed. What else did nothing? The nitrate, there's 2 nitrates here with a -1 charge, and there's 2 nitrates here with a -1 charge. They did absolutely nothing. They sort of sat around and watched the reaction happen, so we call them, those are my spectator ions. So what I end up with are 2 silvers that are aqueous and 2 bromides that are aqueous, and these guys turn into 2 silver bromides that are solid. That's the only thing that happened in this chemical reaction, is I made silver bromide. Can I now make myself some magnesium nitrate? What would you do?
Boil off water.
I'd probably just filter it out, right? If I filtered this, what would filtering do for me?
Separate solid.
The silver bromide would be removed, right? And then I'd have water that's got magnesium nitrate floating around it. Then I'd boil the water off, and what I'd be left with? Magnesium nitrate solid. That's how you make solids that you don't have. You mix things together and then filter the things out that became solids and then boil the water off, and now you got the solid. So if I needed myself some magnesium nitrate and I only had those two compounds, it would work out for me. But what if the compounds I had were magnesium bromide and silver chloride? Would it work for me? It wouldn't. Why not? The silver chloride would never separate. So I'd get the magnesium bromide in the water and it'd separate out, but but I could never get the other piece to let go off of the silver. The silver wouldn't let go of it because it's not a soluble compound. Okay. Questions on that one? No?
So, okay, I have a question.
Yeah?
It is impossible for you to mix solids and get different solids, so if you have only ionic compounds, then you just get to assume that it's in water.
For the most part, yeah.
Okay, so, is that the only thing you're gonna give us, or do you need for the most part?
For the most part.
So, well, like in a test scenario, are you gonna explicitly say this reaction is happening in water, or
Nope.
do you need to assume that?
Depends on the situation.
Okay, I don't understand then. What situations would it not be the case?
We'll talk about it today.
Okay.
We haven't gotten to it yet. Okay, so combustion of propane. So what's the propane molecule look like?
Oh, wait.
And it's combustion, so what do I need? And when I burn a hydrocarbon, what do I get? And the states for these things? Let's just write everything down as a gas. That works. And balancing it.
Three.
That look good? Hydrogens are balanced, and the carbons are balanced, and then there's 4, and there's 6, and so the oxygens are balanced. Okay. All right, so I'm going to start off with 25 grams of propane, and I want to know how much water I can make when I burn this propane. So 25 grams of C3H8. So I need to put C3, C, not H, C3H8 in the denominator. Why does that need to go down there? I need to cancel it out, so it's going to have to be down there. So what do I put opposite that? Moles of C3H8. Okay, so where do you get the mass from for a mole of C3H8? Table. So you got 36 from the carbons, and you've got another 8 from the hydrogens. So you're somewhere around 44. All right. So there's a mass of 1 mole of propane. So this first unit conversion, what did it actually do for us? Okay, so what did it do? What'd you say? Okay, it canceled, but what do we get out of this? I go from a mass, and then I did what to it?
Get a number.
I counted it, right? Isn't that what happened? So I counted exactly how many how many propanes I had here. Okay, so now I know how many propanes. So the bike analogy is now I know how many bike frames I have, and now I need to figure out how many tires I need. So now I know how many propanes I have. Now I need to figure out how many water molecules I can make. And so then I'm going to take my moles of propane. Why does mole of propane go right down here at the bottom? Needs to cancel out, right? Erase. And we're looking for water. And what numbers go in front of the moles? the coefficient. So a 4 for the water and a 1 for the propane. Okay. So what did this just do? So this conversion counted my number of propanes. And what's this next conversion do? Counts the number of water molecules I'm going to get, right? If I stopped right now and did the calculation, I'd have a number of water molecules. Is that useful? Probably not, because when are you ever going to be able to count them? Never. The only way you can count them is to mass them out. So then we're going to switch that over to moles of water and grams of water. So what is it, 18 point something something something?
153 or 0153.
0153? That sounds good. And so now I've got grams of water. And what did we come up with? Around 40?
40.8547.
So 41 with sig figs, since we only had 2. We good with that? Okay.